name is Terry Paxson-Pearson, and I'm a graduate student at the NSCL at Michigan State University. And I'm going to talk about some recent work I've been doing in the realm of charge exchange reaction theory. I'm touching on a new code that I'm developing called CHEX, charge exchange. And I'm going to begin just by thanking my collaborators, so my advisor, Philomena Nunes, and also Gregory Patel, who's also at the NSCL. So I'm going to give you an idea of why JINA community should care about charge exchange reaction theory. I'll talk about sort of the current state of the theory and where we'd like to go. And I'll show you some first results from this new code CHEX and talk about what we want to explore in the future. So charge exchange reactions are isobaric transitions. So that means the mass does not change in your target, but you have a proton converted to a neutron or vice versa. So the most basic type of transition is this PN type reaction. Proton comes in, neutron goes out. Or you can have the inverse, which is a neutron comes in, proton goes out. For lots of different reasons, experimentalists often use composite probes. So helium-3T gives you the same effect of a PN reaction. And in particular, because neutron beams are harder than proton beams, DPP is often used for the NP direction. There's a wide variety of applications for these types of reactions. Of most interest probably to this community is in supernova, core collapse supernova, you have a series of electron captures. And these captures can't be probed experimentally very easily, but it uses the same process as charge exchange, so we can use these reactions to probe that process. And we can also use it to probe various aspects of exotic nuclear matter, so neutron stars. But charge exchange reaction theory is underdeveloped. We use a series of assumptions that restrict the region of validity to high energy, which I define as about 100 MeV per nucleon. But we don't always want to run our experiments at those energies. So a good way to think about it is when you run an experiment at low energy, you really probe the outer tail of the wave function. And as you increase energy, you move further into the nucleus. So we can say, for example, one energy regime is best to probe isobector densities, so the difference between the proton and neutron distributions. So there's a recent work that sort of looked at this problem, where they simultaneously fit proton scattering, neutron scattering, and electron capture. So here we have just the scattering, and this is the electron capture. And he changed, this is work by Danilovich et al., and they changed the optical model parameters, so basically the shape of the potential that describes the interaction, and in particular they changed the radius. And then from this they were able to look at the differences in the radii for the different processes and extract a neutron skin thickness, which can be useful in looking at neutron stars. So what you have here is in the black dots are the neutron skin thicknesses that they extracted compared with a bunch of theories that have no input from data. So this is a theory that is informed by data that we can use to discriminate between pure theories. But if we want to run at these lower energies and do these interesting studies, we really do need a sound reaction theory. So what currently happens? So currently the formalism uses single-step DWBA, which basically means everything happens at once. It's one short process. And this actually gives you reasonable agreement with data for high energies and small angles. So this is recent work by the charge exchange group at MSU. And this is for the case of just nickel-58, helium-3T, a cross-section at very small angles. And you can see the black dots are data, and they're described very well by the theoretical lines. But there is an overall normalization issue with these calculations. But there are limitations to what this can describe. So like I said before, we'd like to go through a larger energy range so we can look at different parts of the wave function. And if we're going at a lower energy, there's more opportunities for more complicated processes. So that means we should go beyond just the single-step process. We also want to use better potentials. So all of this work uses the phenomenological Love and Franey potential, which was an NN potential that has a large uncertainty and is best constrained at high energies. So it's even worse at lower energies. But we'd like to use perhaps microscopic potentials and explore non-local potentials, which I'll talk about later. And we also just want to include more physics. So for example, the deuteron is a very weakly bound nucleus. It's only bound by 2 MeV, and there's a very large probability for it to break up in the field of your target. In other kinds of nuclear reactions, we've seen that has a big effect in our cross-sections. So we want to see if we get the same effect here. The current codes on the market, however, are legacy codes, which were not built with this or really any adaptation in mind. So we decided it was best to start from scratch and build a new adaptable framework. So when you build something new, you have to start with the most simple case. So we're beginning by reproducing DWBA PN reactions for what's called a Fermi transition. This is when you change the isospin, so the numbers of protons and neutrons, but don't change the spin of your nucleus. But it's worth saying that NP and Gamow-Teller transitions, which do change spin, are a straightforward extension of our formalism. My group does every problem in a few-body framework. So, like we talked about a little earlier in the introduction, it's too hard to describe all of these nuclei. We can't do it in an ab initio, a from-scratch kind of way. So we turn our target into an inert blob with a valence neutron in the PN case. We have a proton coming in, and then in the outgoing case, these two switch places. Initially, we're using something called the lane potential, which is difference between a proton and a neutron scattering potential. It's phenomenological. We're doing this because of the work that we're comparing to, but it's worth saying our formalism is not restricted to this potential. It can use any sort of NN potential that you want to give it. So this is the expression for the cross-section for our charge exchange reaction. It has a bunch of factors, but the meat of it is just right here. This is the matrix element where you have your incoming wave function, some interaction, and your outgoing wave function. These wave functions come from a non-local Schrodinger equation solver. So this is just normal Schrodinger equation solver that can handle the non-local potentials that I'll talk about a little bit later. That was developed by a former member of my group. In the most general case, this interaction is an NN potential that sums over all the target nucleons. We have something that can take into account anti-symmetrization. And then we have our Fermi operator, which I said changes isospin but not spin. We actually make this a lot easier on ourselves because we're using this lane potential. So this just runs over one scattering coordinate. It only works with, it takes your nucleus that's a core plus a valence and actually just turns it into one blob. So this is a very, very simple interaction that we're using. A few words about the code itself. So it's CHEX for charge exchange. We really do want this to be a tool for the experimental community. So we're trying to start with a very modular, user-friendly design from the get-go. There is a front end in which the user can say what kind of potential they want, what kind of transition they want, and then that's read into the program. We use this non-local Schrodinger equation solver to get our different wave functions. We can use any sort of potential, and then we just calculate all the necessary integrals in math to give you your final cross-section. So CHEX is currently being benchmarked with that recent work by Danielovich et al. That I showed you earlier. So he has this case where the target has no internal structure, just got one blob. He only looks at isobaric analog states, so that means we go from a 0+ target to a 0+ target. We don't change that spin, and like I said, we're using this lane potential. The first case we looked at is calcium-48 PN at 35 MeV per nucleon. So here you just have the cross-section. It's an angular distribution, so this is the angle. And you can see that for the case of a spinless projectile, we have perfect agreement. That's obviously not physical. Protons have spin 1/2, but it greatly reduces our calculation and helps us pinpoint problems. When you include the spin, we have a small difference, but that just has to do with choices that Danielovich's group made for the purposes of their experiment. We are formally the same. And this shows you the data. So we're in agreement with the shape, but not the magnitude, which is what we expect. So, once CHEX is fully benchmarked, we can actually begin to explore new physics. So the first thing we want to look at is the effect of what I'm calling the single particle structure. So instead of this being one blob, we have this valence nucleon. How does that additional degree of freedom affect our results? Does it give us a better or a different description? We also want to look at the effect of non-local potentials, which we did in my group for a different kind of reaction, and it had quite a large effect. So when I say non-local potentials, what I'm talking about is very closely tied to our introduction. So we know that nuclei are quantum mechanical objects. So we cannot look at the potential that looks at one proton coming on a classical trajectory and only interacting with one neutron. That's not actually what's going on. So because of that, we have to use potentials that actually take into account interactions at all places in space. And these are more complicated, and they take a more advanced solver. But because that was already developed by someone in my group, we've already incorporated that. So right off the bat, we can start to look at these effects. Once we've sort of explored this realm of interactions using Fermi transitions, the first thing we'll do is go on to Gamow-Teller transitions. There's a lot of rich physics that we can start to probe there. So that's when you can start looking at changes in spin. In the long term, we'd like to include multi-step processes. So at these lower energies, there could be opportunities for things like multiple scatterings happening, and we want to see if that has an effect. We also want to incorporate composite probes, so things like helium-3T and the breakup of DPP. So with that, I just want to say thank you, and I'm happy to take any questions.